Hi, my name is Jackson Dahn. My mentors are Dr. Elizabeth Bierman and Dr. James Steck, and I'll be presenting the project that we're calling the Q repeater, which is the quantum neural network training of an n-qubit swap gate. So the first thing is some background. What is a repeater node? Classical repeater nodes are signal amplifiers that are embedded in long-range communication systems currently, such as things like fiber optic internet. And how a classical repeater node works is that it takes a signal and copies it and then sends that down the line. But there's this thing with quantum information called the no cloning theorem, which states that you can't copy quantum information. So classical repeater nodes destroy any quantum information that might be present in signals. So a quantum repeater node is something that does what's called a swap operation, which is that it takes an incoming qubit A and swaps the state of qubit A with an outgoing qubit B. So for our system, we modeled the system with a Lagrangian form of the Hamiltonian using parameters that were called K, epsilon, and zeta, which are the tunneling, bias, and coupling parameters of the qubits. And these qubits these parameters are what are actually trained with the neural network. So those are what act as the weights. And then after we constructed the Hamiltonian, we construct the system of qubits in its density matrix format and integrate the Schrödinger equation using our own integrator that we developed specifically so that we could implement random noise in the simulation. And the noise system that we used is a quantum depolarizing noise model. And so, I'm sorry, and at each time the integrator is queried, we use a different set of random noise to make the system even more realistic. So after that, we constructed the neural net. And so for our neural net, we used a Levenberg-Marquardt learning algorithm. And all of the parameters of the learning algorithm were found numerically. Specifically, finding the Jacobian matrix was found numerically using small changes in the error and calculating a numerical derivative. And our output for the system was called the quantum infidelity of the system, which is 1 minus the quantum fidelity of the system, which is a measure of the closeness of the target state to the actual final state output. So for our simulation methods, we coded everything up in MATLAB because we have some very large arrays, and that makes array handling much easier. The Schrödinger equation we propagated through our own custom fourth-order Runge-Kutta solver, and again, we did that specifically so that we were able to implement that random noise exactly how we wanted it. And then our noise model, we used the MATLAB built-in random functions, but we set the random noise to be seated at the system time so that every single time the integrator was queried by the neural net, it was a different set of random noise, which is the most realistic that we could get with our simulation. So our results so far, we have demonstrated the scalability of the system via what we're calling transfer learning. So what that means is that we were able to train the system of 2 qubits and find those trained parameters, and then from that we were able to transfer those parameters to a set of 4 qubits, 6 qubits, and 8 qubits without needing much or any additional training, so that this system is scalable for any number of qubits that are coming in. Right now, we're still working on the noise model and testing the robustness of the system, but right now we are seeing some trends, which are that the more the larger the system of qubits, that is, the more incoming and outgoing qubits, the higher the robustness of the system, or the better, the more robust to noise that the system is. And that couples with past results we've seen, specifically in the result of an entanglement witness, where we saw similar patterns in the noise robustness. And the interesting part to why we think that the robustness goes up as the qubits increase is an increase in what we're calling the non-pairwise terms. So theoretical results would the pure math would say that certain qubits should have nothing to do with each other, but we're finding that when we add noise to the system, the parameters that do couple those terms are becoming non-zero, so that those qubits are interacting with each other, and that is what is providing the extra robustness. So here we have Table 1 and Figure 1, which are trained noiseless values, and then a graph of those coupling terms. So first, the table, the RMS that we're using is the root mean square error of each of the individual errors from a training batch, the RMS of those. So we use a standardized training set for each of the numbers of qubits, consisting of the charge basis and several other sweeps of relative phases between the qubits. And as you can see, even with the train values, it's very close to unity already. And then the graph here, this is demonstrating what I'm showing with the non-pairwise terms, so that those blue lines are the pairwise terms, which are what you would expect to be coupled, I guess, to have non-zero values. And then those red lines are the non-zero, those red lines are the non-pairwise terms, which theoretically should be zero, but we're seeing when we add noise are not, and are training to higher and higher values. And then these plots here are K and epsilon for the system of 4 qubits, which are the other two parameters that we trained, which are important. But really the importance of these graphs are just to show both the form of each of the parameters, which is sinusoidal over this time period, and then that all the qubits have very similar coupling and parameter terms, but not exactly the same, which is interesting because theoretically they all should. So to wrap it up, so our noisy training is still going on to test the robustness, but we are seeing trends towards more robustness at larger systems of qubits. We have already demonstrated the scalability of the system via our transfer learning, which was one of the main goals of the test. Our simulation is what is considered offline learning, which means that this cannot be directly translated to hardware. Our run on hardware, we would need to input more specific parameters and have it run and have it trained still offline, and then run it online without being able to train it. But that is something that other systems, like industrial systems, use already, and that's not an issue generally. And then finally, to kind of bring this back towards the repeater nodes at the beginning, so what if we have a result that shows a very robust system, that means that in the future, quantum repeater nodes could be implemented with much less sophisticated hardware, and that the software could handle all of the noise, which would vastly speed up the timeline of when we're able to get quantum hardware in the ground in things like these fiber optic cables. And with that, I will open for questions. One application of this that uses these repeater nodes would be what's called quantum cryptography. So one thing is basically our current cryptography for all of our internet and all of our data is based off of mainly two algorithms, which are factoring large numbers and taking inverse logs of numbers, which are very hard to do for classical computers, but are very easy to do for quantum computers. So when quantum computers are at a point where they can factor those large numbers, they will be able to break cryptography very easily. And so there are several algorithms that are developed that are quantum cryptographic, which means that quantum computers cannot break them. But for all of those algorithms, you need to be able to send packets of qubits over very long distances, potentially. So to get a cryptographic key from a lab in California to a lab in New York, you need to physically be able to send those qubits that long of a distance. And so you would need a data transfer system in place, such as fiber optic cables with quantum repeaters in them that can send those qubits over very long distances. Dr. Bierman Dr. Bierman at the university really blew my mind when I took her first quantum class, and I just had to get more and more of it. And then as I learned, the more I learned, the weirder it got, and that's more interesting because you don't. It's never fun to mess with something that you necessarily fully understand and you know how it all works and stuff. And there's so much that's different than anything else I've learned in my education as an engineer or in physics or anything else like that. So.